Hey, welcome back. This is now 9.4. We're worried about comparison, the comparison tests. So basically, you'll get a series that kind of looks like maybe another series that you know whether it converges or diverges. So, for example, last time we learned about the harmonic series, which is divergent. Okay, so from n equals 1 to infinity. So this is the harmonic series. So it's a p series with p equals 1, but divergent harmonic series. Okay. So we know that as a fact. And let's say we are given in the homework the following kind of problem: n equals 1 to infinity of 1 all over 3n plus 5. This kind of looks a lot like the harmonic series, but not really, all right? Because it's moved by 5 and multiplied by 3 in the bottom. So not quite. But is there a way to kind of compare this new series to this old series and then make a statement from that observation? And it turns out, yes, there is. Okay, there's two types of tests you could do. The first one that we're going to look at is the direct comparison test. And then the second one we're going to look at is the limit comparison test. Okay. One thing that's already sort of true that I gave in my section maybe 9.2 towards the end, so you probably were kind of like, oh, whatever. Something that we kind of assume is already true. We're not talking about series like this. Okay, 1 over 3n. From n equals 1 to infinity. This is automatically divergent because it's just a constant times the harmonic series. It's just a series of 1/3 times 1 over n from n equals 1 to infinity. So it's automatically still divergent. Okay, it's a constant multiple of the divergent harmonic series is divergent. Okay, so this is not what we're talking about. Also, what we're not talking about is things like this. N equals 1 to infinity, and let's make it even more kind of evil. N equals 0 to infinity of 1 all over n plus 1. Okay, this is exactly the same as that. If you were to expand, look at the harmonic series when you expand that. So if you plug in 1, you get 1 over 1. You plug in 2, you get 1 over 2, etc. Look at this series. If you plug in 0, you get 1 over 1. If you plug in 1, you get 1 over... Oh, it's the same thing. Okay, so no, we're not really talking about that. We're also not talking about kind of truncated versions. So if you start at n equals 5 to infinity of 1 over n, that thing's still going to diverge. Okay, so if you multiply by a constant, it does not affect whether it diverges or converges. If it originally diverged, like we see in our example here with the harmonic, even if you multiply by a constant, it's still going to diverge. Okay, this one is just kind of a silly example, but this last one is also, if you take away a couple terms, it's still going to diverge. Okay, if you add in a couple terms, it's still going to diverge. Likewise, if it was already convergent, so if you're talking about like 1/2 to the n, which is a convergent geometric series, going from, we usually start at 0. Is that true? I think we usually start at 0. If you started this thing instead at n equals 5, it's still going to be convergent. Okay, so adding in or subtracting a couple terms will not affect the behavior. Okay, so these are both convergent. It might affect what it converges to, right? Because this guy is going to be less than this other guy. This definitely is less than this sum up here. Okay, so it affects the actual value of the sum if it's convergent. If it's divergent, it's still going to be divergent. Okay. So anyways, we're not talking about that stuff. That stuff is kind of already done. Okay, we've already dealt with that kind of stuff before. We're dealing with these other ones where it kind of looks like they're the same, but you're still not sure. Okay, that's what we're up against. So, anyways, hopefully that's kind of established. The way the direct comparison, so let me give you the direct comparison test. So this is theorem 9.12. I think it's 9.12. It used to be the direct comparison test. Okay. So we we're dealing with two series, okay, and we want the terms of both series to be positive. For this test to work, it just has to be that way, and you'll see it when we go through the proof. Okay, so not only that they're positive, so they're not equal to 0, but also that there's this inequality that holds eventually. Okay, so for all n eventually. Okay, so if that holds true, then you could say first, if one of the series you know of diverges, and that series is below the other series, so to speak, the terms of that series are less than or equal to the terms of the other series, then the other series will diverge. It's kind of forced to be divergent as well. Okay. Secondly, if the sort of the bigger series diverges, then the smaller series will, if the bigger series converges, then the smaller series will converge. Okay. The best way I think of describing this, and we could go through the proof, and the proof is in the book, and the proof kind of helps you see why we have these criteria. You know, and I've had teachers tell me, as when you're dealing with proofs, play around with the criteria and kind of see why it has to be that way. You know, try to make up an example where the terms of the series may not necessarily be ordered in this way, and see what happens. But I think for this case, instead of going through the proof, I want to relate it to improper integrals. Okay, so there's actually a comparison test for improper integrals. Okay, so I'm going to kind of explain this theorem by talking about improper integrals. Okay, so this is not a proof, it's just more of an explanation, or to hopefully give you some intuition, because you know how improper integrals kind of work. Okay, so let's say we have a function, some sort of function, f of x, okay, and then some other function g of x, which is kind of ordered in this way. So in this case, f of x is less than or equal to g of x, and of course f of x is greater than 0. Okay, so we want to consider the sort of infinite integrals of those things. Let's go maybe from 1 to infinity, right? Okay, so the integral from 1 to infinity of f of x dx. Let's say that is divergent. So suppose this is true. In that case, what is that saying? Well, it's saying if you try to add up the area underneath the curve of f of x from 1 to infinity, you're going to get a huge amount. And no matter what amount you give me, it's going to be bigger than that, right? So what does that tell you about the area underneath the graph of g of x, which is all of this? Well, g of x, the area underneath that, which we can give the symbol, so suppose that's true, then sort of this integral represents the area underneath g of x from 1 to infinity. That area is more than the area underneath f of x. So if f of x is kind of like infinite, it just forces the area underneath g of x to be infinite. In other words, that will diverge as well. Okay, so that's this case here. If you have a series a sub n that's kind of below, so you know, in our example, f of x is the a sub n and g of x is the b sub n. So we had this inequality where f of x is less than g of x, and when that's true, then the integral of f of x, if that diverges, it'll force g of x to diverge. And likewise, if the summation diverges, then if the series a sub n diverges, then the series, and that should be b sub n, sorry. Okay. Then the series b sub n diverges. Notice here on the other hand, suppose this integral from 1 to infinity of f of x dx converges. In other words, that white area that underneath f of x is finite. You really can't say anything about g of x, because that area under g of x could be finite, but it could be infinite. Okay, so in that case, then the area sort of underneath g of x dx may do one or the other, may converge or diverge. So you have to be a little careful with this theorem. You can't necessarily say if the series a sub n diverges, or rather if the series a sub n converges, it doesn't necessarily mean that the series b sub n has the same behavior. It just doesn't. Okay, it could go either or. Okay, so that's kind of the first case. The second case is then supposing that f of x, g of x is convergent. So suppose then the area underneath the graph of g of x dx is finite, so it converges to some number. So this red area is some finite number. What can you say about the area underneath f of x then? Well, obviously it's less than g of x, so it's going to be some number less than this integral. So it's also going to converge. So you kind of think of convergent as going to a specific finite number. Divergent is going off to infinity. Okay, so if this g of x converges, it's going to equal like 18. So that kind of forces the area underneath f of x to also converge. So in that case, then the integral from 1 to infinity of f of x dx will also converge. And then it means that the series will both converge. So in our example, b sub n is the g of x, the guy on top. If that's convergent, then the series underneath it will converge. Okay. And again, you could also make this other statement if you suppose that the area underneath g of x is divergent, you really can't say anything about f of x. Okay. So suppose that thing diverges, then the integral from 1 to infinity of f of x may either converge or diverge. Okay, so you got to be a little careful using this test, and by all means, please read the proof in the book if you get a chance. Let's go ahead and kind of dive in here and look at one that hopefully illustrates this process. So when you're using the test on my tests in class, I want you to kind of show 3 things. Okay, so here we are. I guess I never set this up with a Roman numeral. Let me do that now. Okay, so this is officially the direct comparison test. Okay. So first, using what do I need to see from you with regards to work? First, I want you to show the inequality holds. So show a sub n is, usually you can just assume it's greater than 0, but show a sub n is less than or equal to b sub n for some n. Then secondly, state the convergence or divergence of a known series. So you're always comparing it to a series such that you know it converges or you know it diverges. Okay. So state the convergence or behavior, let's just call it behavior, so I don't have to write convergence or divergence. State the behavior of your known series. And then thirdly, make your conclusion. So on the test, I should see all of this, 1, 2, 3. Okay. That first kind of fact is kind of maybe hard for some of us to show if you've not taken like a proof type class. It's a direct proof is what you need to use. So anyways, let's look at an example. Okay, so an example here, the sum n equals 1 to infinity of 1 all over 2n minus 1. So this looks like a divergent harmonic. That's what we're thinking, and that's what we're going to compare it to. Okay, but anyways, first off, what we need to do is this inequality type deal. Okay. So I'm going to take 1 all over 2n minus 1 and compare it with something. So how do I get that something? Well, I'm going to kind of just cut off everything except that lead term. It's kind of like what I taught you to do with limits. So on the other side, you're just going to write 1 over 2 to the n. And then hopefully you'll know the convergence or divergence of the series that has those terms. Okay, so anyways, we're gonna say that 1 over 2n minus 1 and compare that to 1 over 2n for n greater than or equal to 1, I believe. Okay, so is that true? Well, if you're doing a direct proof, you can build up from this original statement, and I wouldn't expect you to do what I'm going to show you. Okay, so this is kind of the official way you would do it. So you would have to start here, and then you would multiply both sides by 2, and then you would subtract both sides by 1, and then you could what have I done? Oh boy. 2n minus 1 is greater than or equal to 1. Okay, on the other hand, let's say, yeah, that's fine. So 2n minus 1 is greater than or equal to 1, but also if you start with n greater than, so in this one we start with n greater than or equal to 1, multiply both sides by 2. Let's start with n greater than 1, and you can multiply both sides by 2 again. So you have 2n, it has to be greater than or equal to 2. So in other words, you don't have an issue with it equaling 0 or being negative or something like that. So what can we do now? We can kind of say, I think it's clear to say that 2n is greater than or equal to 2n minus something, right? I think that's kind of, that's obvious, right? And then you could divide both sides. So you could divide both sides by 1 over 2n minus 1. And then this would be greater than or equal to, divide both sides by 2n. Okay, so long story short, the inequality should be greater than or equal to. I'm not even really impressed by my little direct proof here. I think it's very crummy. But you would have to argue something along those lines. Okay, so show that these things are positive and therefore greater than 0, and then you could multiply both sides by the reciprocals, starting from this original inequality, which I think is clearly true. Okay, so 2n is clearly greater than 2, which is then greater than or equal to 2, which is then greater than 0. So if you start with that idea, something positive, and you subtract away, well, anything you subtract away something, it's going to make it smaller. So yeah, 2n is definitely greater than or equal. But anyways, I'm not going to expect you to do that kind of thought. Okay, that thought process would be nice for like a proof class or something like that. We're not going to spend hours upon hours doing little proofs like that. So, and usually I think they're kind of obvious, right? So what's going on here is that in the denominator, I've kind of added 1 in. So it's 2n minus 1 plus 1. In other words, I've made the denominator bigger. And if you make the denominator bigger, what happens to the overall? it makes it smaller, right? So the thing on the left is bigger than the thing on the right because the denominator is bigger. Okay, you could think of it that way. You could also kind of just multiply both sides by 2n, and you'll have 2n all over 2n minus 1, and that will be compared to 1. So obviously the numerator here is bigger than the denominator, so it must be greater than 1. Okay, so that inequality will hold. Okay, so once you're, I would want to see this. This part is what I would want to see on the test. All that other stuff, I don't need to see it. Okay? Well, I need to see your statement of where it's greater than. Okay, so I need, 4 n greater than or equal to 1. Okay, okay, great. So that's your first statement. Then your second statement, you need to say something about this thing you're comparing it to. Okay. So you need to mention, is the series 1 all over 2n convergent or divergent from n equals 1 to infinity? This is divergent, right? It's a constant multiple of the divergent harmonic series. And that implies it's convergent. So you need to say that. You can't just write down, oh, here's my series. You decide whether it's convergent or divergent, because I don't know. No, you got to tell me. Okay. Then thirdly, let's see what we got. So the guy on the bottom is divergent. That means the guy on top is forced to be divergent as well. So we can make our conclusion. The series that's given is divergent. Okay. Okay, let's move on to another example, which is extremely similar, but sort of fails. Okay, so it's the sum from n equals 1 to infinity of 1 all over 2n plus 1. Okay, instead of minus 1, let's go plus 1. And let's naively do the same thing, right? So we have 1 all over 2n plus 1, and then if we get rid of the plus 1 part, we can just compare it to 1 over 2n. And then secondly, the series 1 over 2n is basically harmonic divergent. And then thirdly, hence both diverge, right? Okay, this turns out to be wrong. And it's because of the inequality. Like if you multiply both sides by 2n, you would end up with 2n all over 2n plus 1, and you're comparing that to 1. So you have something smaller over something bigger. That means it's less than 1. So this inequality is going in the wrong direction because the guy on top, the series 1 over 2 to the n, is divergent. But that doesn't tell you anything about the series below it. So which case are you in? You're in this case right here. Okay, you have basically the area underneath g of x diverging, and g of x is above f of x. So you know that red space is infinite, but it doesn't necessarily mean the f space is also infinite. It could be convergent. So that's the issue here, and you can't do that. Okay, it just, no, sorry, buddy, that proof won't work, kind of. Okay. So what do you do instead? Okay, so the other trick you may have seen if you're more of a computer science person, instead of decreasing the denominator, instead of taking away the 1, what you can do is add something in. So if n is greater than or equal to 1, we can take this denominator and rewrite it as 2n plus n, because then our n is going to be greater than this 1 over here, okay, because n is greater than or equal to 1. Therefore, we've increased the denominator on the right, and therefore the thing on the right is actually overall decreased. Okay, so the inequality type then becomes the type we want, and then we could go through with our proof, right? Because now, in the second statement, the series we're looking at is 1 all over 3n. 2n plus n is 3n, by the way. So that series there is harmonic divergent. It's just a constant multiple of the harmonic series, which is divergent. And then we have the proper alignment, right? We have the guy on the bottom diverging, and it forces the guy on the top to diverge. Okay, so the original series 1 over 2n plus 1 is also divergent. Okay. Usually in my experience, the hard part is just setting up that inequality, finding something to compare it with, and then the rest is easy. So we can look at, there's other kinds of problems, like this one, the series of 4 to the n all over 5 to the n plus 3. Okay, so let's consider that from n equals whatever to infinity. Let's say, I guess 0 to infinity. So first I'm going to compare it with a known series. So when you do this comparison, it's not the series you're comparing, it's the terms of the series. Okay, so you have 4 to the n, if I can get my pen to work, 4 to the n all over 5 to the n plus 3. And then you're comparing that. So this time I'm just going to reduce the denominator, and I'll have 4 to the n all over 5 to the n. So you just cut out that plus 3 part. Basically, you subtracted away 3, so you reduce the denominator, so you've increased the overall expression, and you have this inequality type. Okay. Secondly, then, the series of 4 all over 5, 4 to the n over 5 to the n is the same as a series of 4 over 5 to the n. Okay, which is, of course, a geometric series. R value is 4/5. In other words, the absolute value of that is less than 1, hence it's convergent. Okay, so you need to tell me that. You need to say what kind of series it is, and whether it's convergent or divergent, and give me evidence to that effect. Okay. All right, then finally, because the guy on top is convergent, it forces the guy on the bottom to converge, so the series of 4 to the n all over 5 to the n plus 3 will converge. Okay. And for n equal to 0, yeah, n greater than 0. Okay. Let's see. Is that true? 1/3? Yeah. Yeah, it's true. Let's look at another one, maybe another weird one. Example, the series of the ln of n all over n plus 1. Okay, so first, the n value is going from 1 to infinity. So anyways, first I do my comparison, right? ln of n all over n plus 1. And compare it to something that seems familiar. So I believe if I just put 1 instead of ln all over n plus 1, this new thing I've created will be less then, because I've reduced the numerator. Okay. And if you think about it, what is the ln of n? So the ln of n looks like this, and it just keeps going up and up and up and up. So eventually it's going to be greater than 1, right? Where does ln of n equal 1? Well, that's where it's equal to e, right? Ln of e is equal to 1. Yeah, okay. So beyond the number e, this thing is going to be true, okay? I believe. For some reason my brain is saying no. So anyways, it'll be true for n greater than or equal to 3. So as long as it's true eventually, we can get away with that kind of stuff. Okay. So e is like 2 point something, right? So as long as it's bigger than that, we'll be good. Okay, and then right, we look at the series of 1 all over n plus 1 from n equals 1 to infinity. That's basically just a harmonic series, but it's missing the first term, right? So it's a harmonic series, it's divergent, harmonic series is divergent. So we have, so that inequality does not quite work for us, right? Yeah, that won't work because the one we've created is divergent. So, bummer. So what do I do? Well, yeah, sometimes you got to go back and play around with it. So let's, instead of messing around with the numerator, let's mess around with the denominator. Let's make it just n, right? So n, and up here we'll have ln of n. And then our inequality, we can make, so I've decreased the denominator. Overall, I've increased this expression, so it'll be less than. I've decreased the denominator, therefore I have, it'll be less than, okay? Yeah, okay. Let's take a look at this guy on this side, this ln of n over n. That thing looks like something I could do an integral test on, right? So try your integral test 1 to infinity, or whatever to infinity, I guess it won't matter. Ln of n over n, x, ln of x over x, dx, so we can go from 3 to infinity. And see what happens to that thing, right? So you need a u sub for the numerator, ln x, du is 1 over x dx, so dx is x du. Okay. So this will become the limit as b goes to infinity of the integral from 3 to b. I'm replacing ln x with u, all over x times x du. This will be the limit as b goes to infinity of the integral from 3 to b of u du. Then we can integrate that thing. So we get the limit as b goes to infinity of, I'm thinking this one ain't going to work out either, is it? U squared over 2. Well, what a nightmare this one's turning into, right? Anyways, that's maybe no, it's not going to work. Well, let's just see. So from 3 to b, and then back subbing, that will be the limit as b goes to infinity. That definitely doesn't work. Of x squared over 2. I'm so sorry. That's going to be divergent, folks. That's also going to be divergent. So somehow I need to get below it, right? How about this? I would say just do an integral test from the beginning. Let's see if I can increase the numerator. That's not going to help. What I want to do is do like an n plus n, right? So n plus n, and then that, I think that'll do it, right? Because then that's going to be ln all over 2n. In this case, going from here to here, I've increased the denominator, therefore decreased that second expression, and then this will be ln all over 2n, ln of n over 2n, and then you could pull off this, because you're just going to go 2 here, 2 here, factor of 1/2. This will end up being a 4, and then this will be a 4, and then that will be divergent eventually. Let's see it in all of its glory. Limit as b goes to infinity, the ln of b squared all over 4 minus the ln of 3 squared all over 4. That first term, ln of b is going to infinity. ln b squared is going to go there faster. So you're going to get infinity minus some number, which will be infinity. In other words, it's divergent. Okay, so long story short, then, the thing we're comparing it to, the series of ln of n all over 2n, this thing from n equals 1 to infinity is divergent. I mean, technically, it's n equals 3 to infinity is divergent, but adding in a couple terms isn't going to mess it up. So ln of n over 2n is divergent from the integral test. Hence, then the original series, because it is above that series, will also diverge. So ln of n all over n plus 1 is also divergent. Okay, sorry about that. I kind of butchered that one on you. Okay, so let's do one more. So in other words, I think the moral of this story is that sometimes you have to try again to get the right relationship. And on top of that, there's going to be times when you're going to build a series such that you may not know its behavior until you do another test. Okay, so usually you're going to be able to compare it to something nice like a geometric or a p-series, but oftentimes it's not going to pan out, and you're just going to have to kind of use another test like the integral test or the nth term test for divergence. I wonder if you could have just used the nth term test here right off the bat, right? So look at the limit of the natural log of n all over n plus 1. No, that wouldn't help, right? Because that would have been 1 over n when you take the derivative of the top and bottom. The derivative of the top is 1 over n, the bottom is 1. That would have been 0, so no conclusion from there. I think I would have, it would have been nice to do an integral test right off the bat, but I don't think that that integral would have been so easy. So converting into this integral, and of course now you increase the denominator, you decreased the overall expression, so therefore we got the appropriate relationship. We found this one's for being divergent. If this is divergent, it forces the other guy to diverge. And yeah, okay, let's look at one more. So example, this thing, 1 over n factorial from n equals, and you could actually start at 0 if you want, 0 to infinity. Okay. Little known factoid about n factorials, they grow faster than any exponential. Okay, so the way of expressing that in shorthand notation is that the limit as n goes to infinity of k to the n all over n factorial is equal to 0. That denominator just gets so huge it's going to overpower any value of k to the nth power. Okay. So just this n factorial is overwhelmingly explosive, and probably in the book they show you an algebraic proof of that fact. I usually can't even do it off the top of my head, but if you look on the internet you can probably see it, find it somewhere. If you really annoy me about it, I could probably figure it out, but it's not off the top of my head. So anyways, we want to do a comparison test, and so what we're going to do is compare this 1 over n factorial to 1 all over some k to the n. So you could use like 2 for k, because k to the n will definitely be less than n factorial for eventually. So you could say for n greater than some value, greater than or equal to, let's say, I don't know, some integer j. That will definitely hold. So if you on one hand have n factorial, in the other denominator, if you put 2 to the n, this thing is going to be bigger, the thing on the right, because you've decreased the denominator, because that n factorial just grows so fast. Okay? And this will be true for n greater than or equal to 3. Or yeah, greater than or equal to 3. Or no, 4, because 3 won't even work. That will be 1 over 6. And on the other hand, you would have 1 over 8. Okay, so that I'd rather have a sixth of the pi than an eighth of the pi. So the 6, that still didn't work. So you have to go out one more. I think 4 will do it. Okay. And you would have to technically prove that, but we're just going to suppose it. Okay. Okay. Secondly, then, the series 1 all over 2 to the n is geometric. The r value is 1/2, which of course is greater than 1, so it's convergent. Sorry, less than 1, so it's convergent. R value needs to be less than 1. So you have a series on top of the other series that's convergent, and force the one below it to be convergent. So hence, the series 1 over n factorial converges. Okay. Okay. Hopefully that'll get you through the exercises. Let's move on to the other tests, which I think you'll find much easier in comparison. So the section 2 then, limit comparison tests, and then maybe I'll look at one from the book. No, I don't think I have time. Okay, limit comparison test. How does this one go? So suppose you have two formulas for the terms of the series a sub n and b sub n, and they're both positive. And you also note that the limit of the ratio is some number that's finite and greater than 0. So the limit of a sub n over b sub n as n goes to infinity is equal to L, where L is finite and L is greater than 0. Okay, in that case, the series will have the same behavior. Okay, so I want to see a proof of this. So one thing, it's from the strict definition of a limit, if you remember all that jazz, basically that limit above says that eventually for any epsilon you pick, so L plus epsilon to L minus epsilon, eventually, there'll be some number called sort of big M, such that when you go past that big M value, all the terms of our sequence will kind of fall in between L minus epsilon and L plus epsilon. Okay. So we kind of have to exploit that fact in our proof. So our proof, here we go. So we're supposing our conditions a sub n is greater than 0 and b sub n is greater than 0, and the limit of the ratio of a sub n over b sub n is also 0 as n goes to is equal to some L number which is greater than 0 and finite. Let me erase that part. Is equal to L, which is greater than 0 and finite. Okay, from here we invoke this strict definition of a limit. Okay, and instead of L minus epsilon and L plus epsilon, let's use big M and little m. Okay, and I shouldn't use an M. Let's just call this P or something. Okay. So eventually, because of the strict definition for a limit, for any m and n you kind of think up, you can find a p-value such that if you go beyond p, all of those terms are going to be bounded in between m and L. Okay, so because, or just say hence, because of this, the limit existing, yeah, so hence, due to the limit, and our strict definition of a limit, we can find some sort of p-value. So for all n greater than or equal to p, this sequence a sub n over b sub n will be bigger than this n right here, and less than this big M up there. Okay. And because a sub n and b sub n are greater than 0, you can make it so that big N is also greater than 0. Okay, and this will happen for some value n. I already said that, greater than or equal to p. Okay. Okay. So in other words, you can multiply everything by b sub n straight through that compound inequality. What you end up with n times b sub n is less than a sub n, which is less than m times b sub n, which is greater than 0. Okay, so what? Well, if then, so supposing the series b sub n will converges, then the series n times b sub n will converge, and then because of the direct comparison test, the series A sub n will well, no, that won't be true. I have to do the other one. So if the series B sub n converges, then the series of M, big M, times B sub n will converge, and thus it'll force the A sub n to converge by the comparison test. Then the series A sub n converges by direct comparison. Okay. On the other hand, if you suppose the series B sub n diverges, then the lower series n times B sub n will diverge, and that sort of forces A sub n to diverge as well. By direct comparison. Okay. It's kind of a neat little proof, but there it is. Okay, let's actually do the direct comparison test. So, yeah, so part A, using the direct comparison test. First, you choose a series to relate it to, such that you know the behavior of the series you're comparing it to. So choose a known series for comparison. Secondly, then, produce the ratio and take the limit. And then thirdly, if the limit is finite and greater than 0, then both series have the same behavior. Okay, so let's look at an example, and this will be your video quiz for the day. Video quiz, 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 video quiz. Okay. Let me mark that in my notes so I know. This is 1, 2, 3. The last question in homework number 6, video homework number 6. Okay, so the way you can pull this off for a comparison is usually just kind of do what I taught you to do for limits and compare it with that series. So we're going to first compare with the series n over n squared is the same as 1 over n, which is divergent harmonic again. Okay, so if we do the ratio of the terms of the series and then take its limit, and it's finite and greater than 0, then both will be divergent. Okay, so let's note the limit. And we have the limit of n all over n plus 1 divided by 1 over n. And it doesn't really matter how you stack them. Like, you have to be really careful about A sub n and B sub n back in the direct comparison test. But here, you kind of just, it doesn't matter. Okay, it doesn't matter if you put one on top or the other on top. It won't matter. So that will become the limit as n goes to infinity of n all over n plus 1 times the reciprocal of 1 over n, which is, there should be an n squared in there, sorry. Times the reciprocal of 1 over n, which is n over 1. So this will be the limit as n goes to infinity of n squared all over n squared plus 1. And then, of course, from what we know about limits, That's just equal to 1. Okay, which of course is greater than 0 and finite. Hence, both of them diverge. Okay. Let's see if I have any other examples. Both diverge. I don't know why I have a period there. I had to go to my book. Look up 9.4. Just want to do one more. Thinking it's always going to be easy. Let's see if there's any in here that are worth looking at. Four, 617, 618. Apparently not. Okay, so let's just look at number, I don't know, something that looks a little different, right? Let's look at number 25. That looks pretty crazy. So we have the sum of n to the k minus 1 all over n to the k plus 1 from k greater than 2. And we have n equals 1 to infinity. Okay. So first, well, this is still kind of easy, isn't it? So first, you're just going to compare it with this series. Okay. So compare with, maybe I should say limit compare, so you don't actually think I'm doing a direct comparison. Limit compare with the series n to the k minus 1 all over n to the k, which is actually the series n to the k minus 1 minus k, which is n to the negative 1. So it's just going to end up being 1 all over n, which is, again, the divergent harmonic. Okay. Then, secondly, note your limit. So we have the limit of, I'll put the other one up top just to show you that it really isn't going to make a difference. So 1 over n all over n to the k minus 1 all over n to the k plus 1 as n goes to infinity. So to divide, it's the same as multiplying by reciprocals. So you'll have 1 over n times n to the k plus 1 all over n to the k minus 1. And then adding exponents in the denominator, you know, n times n to the k minus 1 is n to the 1 plus k minus 1. So you have n to the k plus 1 all over n to the k. And then, you know, taking the limit of that, it's just 1, which is greater than 0, which is, and also finite. And hence 3, both series diverge again. Let me just find one where they don't necessarily both. So I want to see a different example. So these kind, 2 to the n all over 3 to the n plus 1, something like that, from n equals 0 to infinity. So first, again, you could kind of just do one of those jobs. So consider then the series 2 to the n over 3 to the n. So we're limit compare with the series 2 over n, 2 to the n over 3 to the n, which is geometric, right? That's just 2/3 to the n. So you have to tell me what kind it is, whether it's convergent or divergent, and then why. It's because its r value is less than 1. Absolute value of its r value is less than 1. Okay. Then secondly, you do your limit. So note limit of 2 to the n all over 3 to the n plus 1 all over 2 to the n all over 3 to the n. which will equal, and it's always n go to infinity, which will equal the limit of 2 to the n all over 3 to the n plus 1 times 3 to the n all over 2 to the n. Right? And then that will equal the limit of 2 to the n times 3 to the n all over 2 to the n times 3 to the n plus 1. If you'd rather, you can write that as the limit of 6 to the n all over 6 to the n plus 1. And then you can do one of these jobs. Even though it's not a polynomial, you could still play that game. And you'll just have the limit of 1, which will equal 1, which of course is greater than 0 and finite. Hence, both are convergent. Okay. So that's true, right? 6 to the n is also equal to 2 times 3 to the n, and that's equal to 2 to the n times 3 to the n. Okay, yeah, so that's true. And then, yeah. Okay, so hopefully that will get you through the homework. If not, you can always send me an email, stop by my office. Also, one thing that helps a lot is Calc Chat. So I know that your answers might be different, but that's where your solution manual is. If I've not made that clear, hopefully that's clear now. So this is the solution manual for your book, the Larson book. And it has all the solution manuals for the different editions as well. So what you do is basically, as you're in WebAssign, there's little numbers on the homework problems. So if you go in the WebAssign, wherever it is here, no, stay signed in. You go into whatever section you're working in. Where are the stupid little numbers? Oh, here, Larson, ET7. 8.5, question 3. So what that means is, so you go to Calc Chat, find early transcendentals, 7th edition. So usually it's down in here. Early ETF 6. Here's ETF. This is just the 7th edition, which is not what we want. Early transcendental 7th edition. Then view. So you're just looking for the problem in that book that corresponds to the WebAssign problem. So which example were we doing? I'm not sure where I lost my little tab thing. So you can find the same problem in Calc Chat. It's just it's going to have different red numbers, right? So this is 8.5. This is chapter 8, section 5. Question 3, and then go. And you see it's the same. It's that problem. Okay. It's just where the heck is it? Here. It's just they use a different red number. Okay. Okay. So hopefully that'll help. If you can't get a hold of me, it's my hectic schedule, and you can't get a hold of the tutor. So there's also the tutoring center, at Tri-C we have a tutoring center. So just Google probably tutoring center Tri-C, and it's in WebEx, just like us. But anyways, there's answers there in the Calc Chat. You can go there. You can email me. There's 100 options, right, at this point. So hopefully something will work for you and get you through the homework and get you towards the test. Okay, make sure though you're writing out the way I want it written out, step 1, step 2, step 3. You got to show all that on the test. Usually on the test I'll tell you which test I want to see. So I'll say, using the limit comparison test, prove that this is convergent, or prove that, determine whether it's convergent or divergent. Okay. But you want to be able to write out your answers like I'm writing them out. Don't just throw a bunch of stuff at the wall. You have to imagine you're explaining it maybe even to one of your classmates who's like a week behind you in this class. Okay, so anyways, hopefully that'll be good enough, and we'll leave it at that, and we'll see you next time.